Now briefly, without going into too much detail, we consider an inductor, which is just basically a coil of wire, often wrapped around some kind of an iron core to enhance magnetic fields. Now, I don't want to get into the physics of it, but what happens is if you run a current through a coil, it creates a magnetic field inside the coil. But there's also the phenomenon called induction, whereby if you change the magnetic field inside of a coil, that creates a voltage. So you're in the situation of trying to build a current by changing a voltage, while the inductor is trying to also create its own voltage that opposes you. Now, you can study the physics of that. That's all I'm going to say about it, except to say that if you close a switch on this circuit, the voltage is going to try to drive a current through the resistor and, of course, through the inductor. That tends to increase the magnetic field inside the inductor, which then resists the buildup of current. And the inductor resists the increase of current with a voltage that turns out to be proportional to the time derivative of the current. This relationship leads quickly to a differential equation. Di dt is going to equal, turns out to a difference between the source voltage and the voltage of the resistor. Without going into detail and deriving that particular equation, the result is that if we close the switch, the current will build toward the maximum current, which is just source voltage divided by the resistance. And the current builds exponentially toward that limiting current. When the current is small, when the time is shortly after throwing the switch, the rate of change of the current is fairly large, which creates a voltage that opposes the voltage of the source. As we get closer to the maximum voltage and the maximum current, the current increases more slowly, which means the inductor creates less of an opposing current. And if you think about it, that's all consistent with the shape of this curve. The fact that the curve is exponential just depends on the differential equation that results from this assumption. And the voltage of the source, and excuse that, I had this thing labeled wrong. Voltage of the source is constant. The voltage of the across the resistor and the voltage across the inductor is going to be equal to the voltage of the source. And I'll just mention that right now I'm talking about magnitudes of voltage, not the signs of the voltages. And if you get closer to the physics of the situation, you'll understand what I mean. But for simplification, I'm talking about magnitudes. And that's really all I'm going to say about it right now. The voltage of the resistor is just going to be equal to the current multiplied by the resistance. So it's going to have a curve that looks the same as the curve for the current. The time scale might be similar, but the vertical axis is going to be labeled in, or is going to represent voltages rather than currents. But because of the direct proportionality between the current through a resistor and its voltage, the curve here has the same appearance as the curve here. The voltage of the inductor, which we have here, is simply going to equal the difference between the source voltage and the voltage in the resistor, the voltage across the resistor, so that the inductor voltage will drop accordingly. If we toggle the switch, we're going to get a current versus time a function whose graph looks something like this. This is very similar to a voltage versus time graph that we got for the capacitor, but keep in mind this is current now, not voltage. So this is the rate of change of voltage. Actually, the rate of change of the charge on the capacitor, which is proportional to the voltage of the capacitor. So the charge on the capacitor in preceding video clips, in preceding discussions, had a shape very similar to this, but this is not a charge or a voltage. This is a current. And current would be related to the rate of change of the charge on a capacitor or the voltage. So we'll make note that this graph here is current versus time, not voltage versus time. That's really my point. And that's something you have to be careful not to confuse. Now if we graph the voltage across the inductor versus time, that voltage is going to be proportional to the rate of change of the current. And the graph will end up looking like this. You see that the current is increasing quickly here and less quickly. That means you have a voltage that starts high but is actually decreasing. Then all of a sudden you have a discontinuous change in the current and in the slope of the graph of the current. It's continuous change in the current, but a discontinuous change in its derivative or its slope. So you have, in the ideal case, an instantaneous switch in the voltage on the inductor, and it becomes negative, again reflecting the negative slope here, and then approaches some limiting value before it switches back. And I didn't draw this graph very well. The voltage will actually cross the this horizontal line here, and it'll actually come back like this. Then it'll jump up, then it'll come back like so, and then it'll jump down and come back like so. You should stop and convince yourself that the slopes of this graph, the derivatives of this function I've shown here, will behave in the way I've shown here. Now this is actually more than you need to know about the behavior of inductors, but I'll push it one step further. If you drive this circuit with an alternating current, a smoothly alternating current, rather than a current that suddenly toggles back and forth or instantaneously toggles back and forth, and I say you're driving it with a current, you're driving it with a voltage that toggles back and forth between positive and negative. If you drive it with a sinusoidal voltage, then you might get a current graph that looks something like this. Now there's going to be a difference in the phase between the current and the driving voltage, and I haven't really depicted that here. Something that goes a little beyond the scope of what we're trying to do here, but not much. And if you then look at the voltage across the inductor as a function of the current in the circuit, the voltage is high when the slope of the current graph is positive, and when the graph is steep, so that we're going to start out with a high voltage. Voltage drops to 0 when the rate of change of the current is 0. That's going to occur at this peak, so we're going to have a inductor voltage that falls like so. And then the derivative, the slope of the current versus time graph is going to go negative and eventually level off. And if you reason out the way these slopes change, that's the way your voltages change, and you're going to end up with a graph like this where your voltage is 90 degrees out of phase with the current, a quarter cycle out of phase, so that the current is 90 degrees of phase ahead of the voltage. Okay, that's the opposite of what happens with a capacitor. And that's going to be significant. I'm going to wave my hands a little bit about this again because I'm not trying to do a physics course here. But in the next clip, we consider what happens if we combine an inductor with a capacitor.